Probability and Introduction to Statistical Inference. Many random variables such as height, weight, or IQ score follow an approximately normal distribution. We frequently use the normal curve to model these distributions, as well as many others. Use of the normal curve requires that we estimate the population mean mu and the population standard deviation sigma. This is notably different than when using descriptive statistics, when we can calculate a known value for x bar and s, which are sample statistics. Assuming values for mu and sigma, we can estimate the probability that a random variable value range will occur, though not a specific discrete value. So on a normal curve, we can estimate the probability that a variable will be 1 less than some value, 2 greater than some value, or 3 between two values. Using the Excel tool Probability and Intro to Inference, we can easily calculate normal probability using Excel's norm_dist function. Tap the Worksheet tab for the normal probability calculator, and then input a value for the mean equal to 20 and a value for the standard deviation equal to 5. Then we can calculate the probability that our variable will be less than 15, more than 25, or between 15 and 25. The blue shaded area shows the probability. Here we can see the probability of less than 15 and the probability of more than 25 are the same, 0.1587. This is because 15 and 25 are both exactly one standard deviation from the mean, one below and one above. Normal probability is a function of z-score. Values closer to the mean have greater probabilities and z-scores closer to 0. Values farther from the mean have lower probabilities and more extreme z-scores. No matter what the values for mu and sigma, if the z-scores are the same, the probabilities are the same. Though there is an infinite combination of mu and sigma values, there is still only one normal curve. This is because normal probability is based on the standard normal distribution, which has a mean mu of 0 and a standard deviation sigma of 1. It is essentially the distribution of z-scores. If we input a value for the mean of 0 and a value for the standard deviation of 1, we can see the same probabilities, 0.1587, except instead of inputting 15 and 25, we would input the z-score, -1 or +1. Our normal probability calculator will also do inverse calculations. Instead of inputting an x value, such as 15 or 25, we can specify a probability and work backwards to obtain the x value. For example, here we can see that the bottom 2.5% and the top 2.5% of any normal curve begin exactly 1.96 standard deviations from the mean. Therefore, the middle 95% of any normal curve covers the range plus minus 1.96 standard deviations from the mean. Let's go to our Excel tool now to practice using the normal probability calculator. Begin by tapping the Worksheet tab for the calculator. Now let's consider that simple example. Let's assume we have a normally distributed random variable with a mean of 20 and a standard deviation of 5. We'd like to know the probability that this variable will have a value less than 15. Our left curve calculates the area under the curve less than or to the left of some value. Here we could see it's 0.1587 with a z-score of -1. Let's try another. What's the probability that this variable will have a value greater than 25? The z-score of 25 is positive 1, which makes our probability, the blue shaded area, again 0.1587. The area between 15 and 25 would be what's left, or about the middle 68%. So about 68% of the time, this variable will have a value at random between 15 and 25. We also looked at inverse calculations. So our bottom three calculators do those inverse calculations using Excel's norms inverse function. We just input the probability. For example, the top 2.5% or 0.025 begins exactly 1.96 standard deviations above the mean, or at the point 29.8. In the lower tail, the bottom 2.5% is 1.96 standard deviations below the mean, or at the point at most 10.2. The normal distribution is a fundamental part of many of our most basic statistical procedures. However, it can be used alone for many practical applications. For example, let's look at our cardholder data. Let's assume that the population of all credit card holders has a mean income of $125,000 and a standard deviation of 45,000. And let's assume further that the distribution of incomes is about normal. So we can use the normal curve to answer probability questions about cardholder income. For example, what is the probability that a randomly selected cardholder will have an income greater than 175? Going to our Excel tool, we would begin with the mean and standard deviation, 125 and 45. We want the probability that a randomly selected cardholder would have an income over 175. The z-score of 175 is 1.11, which makes the probability 0.1333. Let's try another. What is the probability that a randomly selected cardholder will have an income less than 75? Now, we don't really need any calculator for this one because we can see that 175 is 50,000 above the mean, while 75 is 50,000 below the mean, which would make the z-score the same and the probability the same. Let's try it on the calculator. Our left curve will calculate the area under the curve less than 75, or 0.1333, and we could see the z-score of negative 1.11. The top 2.5% of all incomes should be at least what value? This is going to be an inverse calculation, and we've now seen that the top or bottom 2.5% begins 1.96 standard deviations above the mean. In other words, 1.96 times 45 added to our 125 will give us the point 213.2. Let's try it on the calculator. In our lower curves, we can input the upper tail probability of 0.025. We could see the z of 1.96 and the income value of 213.2 calculated for us. One more. The middle 95% of all cardholders will have an income between what, min, and max. So we already know the max is 213.2. Because if the top 2.5% begins at 213.2, the middle 95% has to go up to that same point. Let's try it on the calculator so we can visualize. If we input the probability 0.95, we can see the blue area begins at the income 36.8 and ends at 213.2. Now let's turn to an important theoretical application of the normal curve known as the normal sampling distribution. Sample statistics calculated from random samples are random variables. For example, in our sample of n equals 109, the sample proportion of women is about 55%. But a different sample would produce a different p-hat value. P-hat is therefore a random variable. It changes or varies from sample to sample. X-bar also is a random variable. The sample mean in our sample of n equals 109 is over $133,000. A different sample, though, would produce a different sample mean. A sampling distribution models, theoretically, the distribution of all possible values of a sample statistic for samples of size n. Though our sample statistics are known and calculated using our descriptive statistics, it's important to recognize that they are just estimates of the true population parameter. Let's begin with the normal sampling distribution of p-hat. The sampling distribution of p-hat will be approximately normal when n is large due to the central limit theorem. We could therefore model the sampling distribution of p-hat using a normal curve. The mean of our normal curve would be an assumed value for p, the true population proportion. The standard deviation of our normal curve would be equal to the standard deviation of p-hat, also known as standard error of proportion. This sampling distribution would model the distribution of all possible p-hat values for samples of size n. The formula shown would calculate the estimated standard deviation of p-hat. It's important to note that all properties of the normal curve are the same. For example, the middle 95% is covered by the range plus minus 1.96 standard deviations. We can use our normal sampling distribution of p-hat to make probability statements. This requires that we assume a value for p, the population proportion, and here we're using 0.5. What is the probability that a random sample of 109 will have a p-hat value greater than 0.5505? We could see the answer is 0.1459 with a z-score of about 1.05. 95% of the time, samples of 109 will have p-hat values between 41% and 59%, and we can see that our p-hat value is well within that range. Note that if we assume a population proportion of 0.5, the range 41% to 59% covers the middle 95% of our sampling distribution model. Now let's go to our Excel tool to see if we could obtain those solutions and discuss the results. To use a normal curve, we need a value for the mean and standard deviation. Here, a mean would be our assumed population proportion of 0.5. The standard deviation would be our standard error of proportion, and it would come from our formula, the square root of p times the quantity 1 minus p over n, which is 109. So our standard error is about 0.0479. Now that we have a value for the mean and standard deviation, everything runs just like it would for any normal probability calculation. For example, the probability that a random sample of 109 would have a p-hat greater than 0.5505 is about 0.1458 with a z-score of about 1.054. So we can see that if the population proportion of women is exactly 50%, our p-hat value would be rather likely because it's only about one standard error above the mean. Let's try another one. The middle 95% of all p-hat values for samples of 109 is about 41% to 59%. And we could see that our p-hat value is well within the range. In other words, if we assume a population proportion of 50% women, samples of 109, 95% of the time should have p-hat values in this range. Now let's look at the normal sampling distribution of x bar, the sample mean. The sampling distribution of x bar is approximately normal when n is large, or at least 30 due to the central limit theorem. The mean of the sampling distribution of x bar is equal to mu. The standard deviation of x bar, also known as standard error of the mean, is estimated with the formula sigma over the square root of n. Let's consider the sampling distribution of mean income for samples of n equals 109. If we assume a population mean of 125, and if we assume a population standard deviation of 45, our sampling distribution would center on a mean mu of 125 and have a standard error estimate equal to 45 over the square root of 109. We can use our normal sampling distribution of x bar to make probability statements about sample mean values. For example, what is the probability that a random sample of 109 will have a sample mean income greater than our x bar of 133,872? And the answer is only about 2% with a z-score over 2. This probability shows that our sample mean would be very unlikely to occur at random, only 2% of the time, if the true population mean were 125 and the population standard deviation were 45. 95% of the time, samples of 109 should have sample means in the range 116.55 to 133.45. Note again that this range covers the middle 95% of our normal sampling distribution. Let's return to our normal probability calculator to see if we could obtain those answers and discuss the results. We're assuming a population mean income of 125,000. Our standard deviation is equal to standard error of the mean, or sigma 45,000 over the square root of n, which is 109. So the standard error of the mean for samples of 109, assuming a sigma value of 45,000, equals about 4.31. The probability of getting our sample mean of 133.872 at random is less than 2%, the very small blue shaded area, because the z-score of our x bar is a little bit over 2. In fact, 95% of the time, sample means for samples of 109, assuming a population mean of 125,000, should be in the range 116.55 to 133.45. Our sample mean is not in that range. So either we obtained at random a very unlikely sample mean, or perhaps the true population mean income is a little bit greater than 125. It's important to see that both standard error formulas have n in the denominator. Therefore, as the sample size increases, the variability in our sample statistics should decrease. This is known as the law of large numbers. In other words, as our sample size increases, our sample statistics get closer and closer to the true population parameter that they estimate.